Hello, everyone. Thank you so much for joining us today for the AIAA Los Angeles Las Vegas section. Very special meeting. This is one for many years, a very special event for the exciting DCXXA project. So we have five very distinguished speakers today with us. So two are here, Jeff and Jim, and three are online, including our Executive Director, Dan. You can see on the lower left corner, and you have Joaquin and Jess. So without further ado, I will just turn it to Dan to start the program. So welcome, Dan.
Well, thank you, Ken. And good evening, good afternoon, whatever's appropriate in the time zone you're at. I come to you from the Eastern time zone, so just want to say hello to everyone and also recognize that there are going to be some people in the audience, either locally or online, that had big parts of this. So what you are seeing is a reflection or is part of the team, not the whole team that made it happen. So I want to recognize all of those that are in the audience for all of their great work to help make this historic event happen. A few months ago, Ken asked me about the idea of having a DCXA event. I thought it was a great, fantastic idea. And immediately asked Ken to go reach out to people like Jess and others to go, let's get the right people and make sure it's representative of the whole program so that we could have the good whole story all the way through it. So what we're going to do today is have Jess and company, Joaquin and Jeff and Jim help go through how this all got started, talk about the DCX phase of things, and then I can come in and talk about the NASA side of the equation. And then importantly is have a discussion about what all was learned from these two projects and how it's manifested in today's new commercial launch systems and where the launch vehicles of the future are headed. I will highlight, in case you can't see, I'm a model collector, in case some of you don't know that. And over my left shoulder is a model of the DCX-A with a hat signed by Pete Conrad. So that Pete actually gave my father, and my father returned to me a couple of years ago. So without further ado, I'm going to turn this over and let Jess carry the ball on how this all got started and lead us into the DCX discussion. And we're going to have plenty of time for Q&A at the end and discussion along the way. So without further ado, Jess, it's all yours, man.
Yeah, absolutely. Hey, Ken, can you put the charts up that we've got? And I assume you're going to turn them as we go? Hey, Ken, are you going to show there you go?
Yeah, it's coming up.
All right. All right. Well, so I'm going to talk, and you can kind of forward to my section, but I'm going to talk to how the program got started originally. And I'd like to point out that although I was over on the side watching it happen, I wasn't a direct participant in the early years, other than what I tell you here. So first of all, the exciting thing, or the crazy thing about this program and its original origins is it started in the basement of a science fiction writer. That would be Jerry Pournelle and Larry Niven. And they had obviously written about access to space and how it's going to be cheap and easy for many, many decades. They had a group called the Citizens Advisory Committee for Space.
Yeah.
And so they met in their basement at what they called Chaos Manor, which is Jerry's home. And they brought a eclectic group together. It included Max Hunter, a famous engineer from McDonnell Douglas days from way back. Jim Ransom, an aerospace corporation guy. I think they borrowed some charts from maybe even Gary Hudson. And they kind of, and I'm sure there was another dozen people involved, but they basically put together a concept for what was called Spaceship Experimental. And it was a single stage to orbit vehicle that they thought could be built and flown for $1 billion. And don't ask for more than $1 billion, but try to get 1 billion. So from there, they kind of wrote it up in a series of charts, and they took it to a company called High Frontier.
Yes.
Yeah. So they took it to an organization called High Frontier with Lieutenant General Danny Graham. And so go to the next chart. There you go. And so you can see Jerry there. I don't have Larry Niven on here. I think Larry's still with us, but Jerry died last year, I believe. And there's a lot of other people here that were involved and were fathers of the program in one respect or another. The ones I have highlighted are no longer with us, but there's many others who are fathers of the program. And if you aspire to have a program, it's really good to have a lot of fathers. And we did. We had a lot of fathers of the DCX program. So they took the program to General Graham at High Frontier. High Frontier was an outfit that was pushing Strategic Defense Initiative Organization. General Graham took it over to the White House with them, and they went and briefed the vice president, which was Dan Quayle at the time. And a note came down from the White House. And usually when notes come down from the White House, they get prompt attention. But it went to the director of SDIO, General Monahan. And he turned it over to his 2 top technology guys, Dr. Mike Griffin and Gary Payton, and to assess and see whether or not we could actually do this. And their interest at the time, or the interest they put together, was a brilliant pebbles system for deploying brilliant pebbles, and also for maintaining that constellation in the future. Which would require frequent access to low Earth orbit. So they started looking at it, and that's where I kind of came in. I was at the National Aerospace Plane Program at the time, and we had developed a program called HAV Region. And we'd spent about a decade maturing the technologies for single stage to orbit all rocket powered vehicles. Next chart. HAV region is on this chart. So it's the one called SSTO studies, but I did want to highlight that this wasn't a totally new idea. You know, there was a Strategic Air Command Statement of Need 779, Air Force Space Command Mission Need Statement 6-84. There, in the future years, there were all kinds of requirements documents for everything from ISR to weapons delivery for this class of flight system. And you can kind of see that there's a history that goes all the way back to the German Sanger concept in World War II, the X-15 rocket plane, the X-24A, the X-24B, even the XS-1, the original version, which later became the X-1, was a rocket-powered plane that first broke the supersonic barrier. So we got a long history of rocket planes that had been developed in the past and that fed into all of this. Go ahead to the next chart. So this was the HAV region program, and this was an interest of Strategic Air Command in particular. They were looking at metallic dual wall sandwich construction vehicles, and they actually built the large structures that you can see on the side. They were all horizontal takeoff, or at least attitude at horizontal takeoff configurations. One of them had a little Rado bottle on it. Another one used a big sled, and the third one actually had an SSME in the nose. That was the McDonnell Douglas version. Took off like the Hawker Harrier. What was interesting is when we built all those structures, they all came within 3% of the predicted single stage to orbit weight budget. Now that doesn't mean you can do single stage to orbit. It means that we had a design and that came within 3% of those weights, but it's pretty impressive. The loads were all validated by fundamental and then by actual test and during this. And all of the articles at some point in the test program were destroyed, but all of them demonstrated the ability to come in at weights pretty close to what you needed for this type of flight system. So we thought, coming out of the HAB region program, which was highly classified at the time, that you could certainly do single stage to orbit. But to be truthful, taking off horizontally with something like this is a really hard challenge. Taking off vertically where rockets have thrust to weights of 100 to 1 or better today, that makes it a whole lot easier, as has been demonstrated by SpaceX in recent years. So we did a great job, and we took that story to Mike Griffin and Gary Payton, briefed them, and they said, this might actually work. So they put a budget together. Now, unfortunately, it wasn't $1 billion. If it had been $1 billion, we would have beat Elon to the punchline. But instead, it was $60 million budget. And that's what we went off to prove and demonstrate. Next chart. And the one thing I did want to leave you with on this little section right here is there's a lot of children of DCX and DCXA, as well as a lot of fathers of the program. And I put a few of the concepts here, but there's obviously a lot more still coming at us. And we're all excited about it and watching all of our children grow up. So I think that what Gary Payton and Mike Griffin did, they put together about a 12-page RFP, and they went out to industry. And Jim French is going to tell you, because I wasn't at SDIO when this part of the program was going on, Jim's going to tell you how we went from there to the DCX and XA. That's my section. Jim, it's over to you.
Well, I can happened. I was it was kind of interesting. Mike Griffin and I had worked together for a long time, knew each other very well since JPL, and he got a job consulting basically to SDIO, who was picking up the single stage to orbit program, and I also left JPL, went to American Rocket, and found out that I didn't lie well enough to be a good entrepreneur. So I became a private consultant, and was working on that when Mike was appointed to chief of technology for the SDIO program, and the people he had been supporting said, well, what are we going to do if you're up there in the front office? What are we going to do for somebody to help us? And he says, I have just the person for you, which turned out to be me. So I was consulting with SDIO when this whole thing got started, and I don't know all the political ins and outs, but from the technical or the hardware side of it, he ultimately wound up with a request for proposal going out to the various aerospace companies to build a test vehicle, which ultimately became DCX. And the idea ultimately was that we wanted to be able to put a very large number of satellites in the thousands of satellites into a various orbits at in a very short amount of time. And we're talking like 6,000. Nowadays, every billionaire that comes down the pike has a bunch of satellites like that he wants to put up. But in this era, back in the 90s, to talk about putting up that many satellites was totally mind-boggling, and clearly would have, using the conventional launch vehicles to put them in a variety of different orbital planes and so on, would have broken the budget. So we rapidly came to the conclusion that what you needed was a reusable single stage to orbit vehicle. You launch it, it goes into orbit, it unloads its satellites into this particular orbital plane. 12 hours later, it lands. We refurbish it, put in a new payload, tank it up, and fire it again into the next target orbit. Now that was pretty much unheard of. Just the whole idea. This, mind you, was in the era when we had the shuttle frame of mind where, yeah, it was reusable, except that when you came back, you had to tear it completely apart and put it back together before you launched it again. This clearly is not the way to run an airline. I was reminded of the comments by the founder of Southwest Airlines when they asked him why he was pushing so hard to cut the landing to takeoff turnaround time and their airliners down to 20 minutes, which was also unheard of in those days. And his comment was, airplanes don't make any money sitting on the ground. So he wanted them to fly as much as possible. And I said, well, we need the same slogan to rocket vehicles, because if we're using them to haul cargo, having them sitting on the ground is not a way to get the job done in an economic fashion. So that basically led to the single stage to orbit reusable vehicle concept, of which we didn't have enough money to build a real orbital vehicle or even try to right off the bat, but there were some things we needed to demonstrate. One of which most prominently was that you could take a complex vehicle that burned LOX and hydrogen, and you could fly it, bring it back, land it, and get it ready and fly it again within a very short amount of time. We chose 8 hours as a target for demonstration, because if you could do it with an airplane, you ought to be able to do it with a rocket vehicle. I mean, yeah, there's the mystique of space and all like that, but the bottom line is they're still flying machines. They're all complicated. They need to be designed properly to make the, to meet the turnaround requirements. So there was an RFP put out. We had, as I recall, 5 bids on it. Predictably, we had Rockwell International was something that took off vertically and landed horizontally, which just coincidentally was the way the shuttle operated, and just coincidentally they built it. Then there was Boeing, who had a rocket sled launch approach, and was horizontal landing or horizontal takeoff and horizontal landing. General Dynamics came up with a vertical takeoff and vertical landing concept, which was one of 2 that was proposed. Theirs was a pretty much a ballistic or very low L/D entry, reminiscent of Gemini or Apollo capsules. And then we had one from McDonnell Douglas, which was an aerodynamic vehicle, a high L/D, relatively speaking, entry vehicle, but which did in fact take off vertically and land vertically. And we of course, went through all the usual procedures, and McDonnell Douglas came out as the winner, hands down, with the concept that ultimately became DCX. And the goal was to demonstrate, 1, that you could do the vertical takeoff and vertical landing. 2, that you could turn it around in less than a day and fly it again after you fly it in the morning and fly it in the afternoon. And we came very close to doing that. Of course, the vertical takeoff and vertical landing was, I never did understand, well, I did understand, but it wasn't technical, about why certain organizations were so dead set against that idea. Because the thing that they flew took off vertically and landed horizontally. And we took some of the most incredible amount of flack in the media from people in the working for large government agencies that have a laboratory at Langley, Virginia, and other places like that, who called us a bunch of hoodlums, which still rankles me because we were the same engineers as they were doing the same job. And the fact that we picked a different scheme than they did was apparently unacceptable to them. So it still kind of burns me. In any case, we had the demonstration of this, and more particularly the 8-hour turnaround. Well, that picture there shows you the vertical takeoff and landing. We flew it many, many times, very successfully. And Flight 5, which we'll talk about later, where we had the damage to the vehicle at liftoff. If that had been an aerodynamic vehicle, we would have lost it on that mission. But even with a hole in its side, it made a successful return. But we also demonstrated 8 working hours from liftoff, or from landing on one mission to liftoff on the other. And that was really remarkable. And I'll throw in one little amusing Pete Conrad story there. We came in the morning, flew it 2 hours after we turned on the power, flew just fine, came back, landed, put it back on the pad. And Pete said, and we were all set to go at like 4:30 or something like that. So he called up range safety and said, okay, we're going again, blah, 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 4:30. And and they said, no, you can't. We're going home. Our shift is over a half an hour before you want to launch. Now, you've heard the term cussing like a sailor. Pete Conrad was a sailor. And boy, howdy, could he cuss. And I heard some words that day that I didn't believe I'd ever heard. But in any case, it didn't move range safety. They will still went home. So we did the next best thing. We got it ready and went home at 4 o'clock, came back in the next morning at 8 o'clock and flew it 2 hours later. So in terms of work hours from landing till takeoff again was 8 hours, 8 work hours, one shift, which was our goal. It's not quite as spectacular when as you split it between 2 days, but the fact is we did successfully demonstrate that. So I'm going to hand the mic back and we'll talk about this some more later.
I guess I'm up. For those online, I'm Jeff Laube, currently with the Aerospace Corporation. But at this time, I was with the McDonnell Douglas Corporation. I was a Delta rocket system engineer and became involved with the DCX program about the time of the proposal. Next chart. One thing about programs is that they don't just happen. The team that put this together had actually learned how to be a great team together. Earlier in the mid to late 80s, we had a series of missions with SDIO to see if we could do some basic research. Could I launch something that could observe another craft in space? What could I see real time? And can I pull off an intercept? That was the Delta 180 program. I know that's my favorite because I designed the orbital ballet. And we did a series of other missions, the Delta 181, Delta 183, Delta Star. And also during that same time, the Delta program was restarted. It had been shutting down because the shuttle was going to launch everything until something called Challenger occurred. Then we had to bring back the program, and it was literally 3 months from Challenger to when the Delta II program came out. So everyone up, the core team on McDonnell Douglas, sorry, the echo's getting to me, worked on 1 or 2 or 3 of these different programs. So when the time came for DCX, we knew how to work with each other. We knew how to work with our subs. We had a way that we worked very well. Next chart, please. Paul Clavat, who was our day-to-day program manager for DCX, set up a series of product teams, making sure that everyone knew what their role was. You can read from requirements, design development, assembly and checkout. we were checking everything from cradle to grave. That was important, that we had a vision, not just working any one part, but what am I going to do when I get it out to the field? Operations was key on this thing. Next chart. Okay, there we go. He created a series of integrated product teams who had specific areas of responsibility. As you can read, vehicle management, all the G&C stuff, propulsion mechanical, engines, tank, structures for his tankage and all that good stuff. And there was an integration IPT where I worked mostly, making sure that all the pieces were coming together and were organized. What was interesting about the way we do it is that anyone could talk to anyone else if they had a question or see something they didn't understand or thought there was something else that should be done. The rule set up by Paul was that anyone can bring anything up, but you have to have the first cut of a solution if you think there's a problem. You just can't say, I don't like that. In fact, that rule was applied to our review teams. So when someone came in, when we had our our initial design review and final design review, you can call it PDR or CDR. If someone came in to review and they wanted to write something up, they had to be the first person on the team to solve it. So that helped us a lot. Next chart. So how we do this? We had lots of performance margin. Since this wasn't going to orbit, we could make it a little bit heavier, so we didn't have to do a lot of extra testing. We had daily meetings and everyone was there, either in the room or on the phone. I had the privilege, I guess that's the word, of running the second year of the meetings. Tom Ingersoll, who you'll see later in the Platypus Control Center monitoring the launches, ran it for the first year. I had the second year leading up to launch. We had a limited number of CDRLs, command data. Come on, help me guys. CDR requirements and logistics.
Contract data requirements list.
Thank you very much.
Yeah.
Voice from above. We had tailored design reviews, IDR and FDR, because we were basically modified preliminary design and final design and design. Things were co-located before co-location was a thing. Rapid short lines of communication. We used faxes. We used the beginning a lot of emails and a lot of telecoms. Today, if we with what we have now, it just would have been much easier. But faxes were key, and we understood what the requirements was. Everyone on the team knew what was required. Didn't matter if you were working on the main engine over at Rocketdyne, Joaquin. You were with another sub. You were as much part of the team as anyone else, and you were just much held responsible as anyone else.
Hey, Jeff, why did you go with the IDR and FDR nomenclature, and how does that relate to the rolling wave that Paul talked about?
Well, the terms PDR and CDR have a certain meaning to engineers. So first, we created a different name simply to say this is different, just to catch people's minds, to understand what's there. But as Jeff mentioned, we had a rolling wave. Basically, we were building all the time. It's sort of like IDR happened at a point, we caught everything that was completed at that time. And we just kept going. We just kept expanding. I remember when we did IDR, we had a part of the building set aside to show all the equipment that we had created, borrowed, stole, whatever you call, to build the DCX. When we got to the FDR, we had full components. We had rocket engine. We had all sorts of things for people to look at. The idea was just to show that this was a real program going to happen, and you have to be part of this as we go forward. Was there anything else, Jess?
No, that's perfect. Basically, it allowed us to do the streamlined acquisition, the rapid prototyping that would not have been possible using a standard PDR, CDR process. Absolutely.
And one unique thing, the rocket engines that we use were, I think, originally RL10 A3s. They were no longer in use. They were in storage, which they were brought out, and they were modified into what we call A5. Hardly any modifications. Changed the thrust chamber, changed the nozzle, add a throttle valve, add a mixture valve, and they were leased technically, not bought, to cut back on the traffic. I think I got that right, Joaquin.
Right.
Okay. Next chart. Okay. And if you could move them out of the way for just a second, please. Thank you. Like I said, we had small review teams. Everyone got familiar with the rapid prototyping process. Everyone felt part of what was going on. So if you saw something somewhere else, you were encouraged to be part of the solution. Even if you were the propulsion guy that has structure question, or you had a guy as G&C section. Like I said, we recommended design solutions. We made sure that each action item was properly tracked and resolved. And we had reviews on an as needed, not just because it's been 3 months, let's have something. On this picture, you can find Jim and I. If you see the gentleman who's squatting down in front and center, right behind him is Jim. If you keep going straight back to that ladder, you see a guy under the middle of the ladder with glasses, with much darker hair. So, well, yours was darker too, I guess. But you know, so this was a tremendous team. This team just enjoys getting with each other even now. We haven't. Hopefully, this year, coming year, we will get back together because we're coming up on the 30th anniversary of the first flight. But we'll keep this. We enjoyed working with each other. I think that's my last chart. One more. Yeah.
Hey, so I've got a question for you on the, with all those folks there, you know, it looks like an unaffordable program. I take it all of them weren't full-time. You know, my understanding was there was a small core group and then a lot of people you reached out for functional support to. Can you talk to that?
That is correct. There's probably about a couple of dozen or so who were the full-time on the team making it happen. Everyone else was on an as-needed basis. But because everyone enjoyed this program so much, when they were needed to come back, they would break anything it would take to be part of it. Everyone enjoyed. There was something special about this program that anyone and everyone wanted to be part of.
And how'd the leadership, Chuck Ordall and that crowd at the vice president level, how were they in terms of supporting it?
They were absolutely wonderful. Chuck was our VP over the program. I was in his office when the call came in from your former boss, Pat Ladner, announcing the award. Ken Francis, the exec director, I was mentioning to Jim, and I can talk about it later. Well, on the first flight, a lot of the people in this picture couldn't be down at the White Sands, but we were allowed one video feed in.
Yeah.
We had a vice president warmed up to keep sending money to keep the satellite links up. But we'll talk about that a little bit later.
Yeah, and I would kind of add to that you know, subsequent to this program, when we went to the Venture Star activity and later when I did the XS1 program at DARPA, we just didn't have the support of the senior leadership. And so for a program that's rapid prototyping, you're going to build it and fly it, you got to have the big boss on board. He wants to make it happen. He needs to want it.
Absolutely.
If you don't have that, might as well wrap it up and go
that's
home. So one more question for you.
Oh, one more.
You forgot Bill Gobbets. Who's Bill Gobbets?
Okay, if you look at the front row next to Jim, can you guys hear me?
Yeah.
Yes.
Can you guys hear? Okay, here we go. Where Jim Mr. French is, to his right is Dave Wensley. So as you move left on the picture there, next to him is Paul Clavat, our DCX program manager, who this wouldn't have happened without Paul. And next to him is Bill Govatz, our program manager. Bill was the prophet. He went out to the field and just kept selling this team. He just kept going forward. I was mentioning to someone that at one period I was working for Bill for about a year, and I put together, I think, 53 presentations in that 1 year period of time. Bill, you know, they weren't all brand new. They were modifications. In fact, I gave I think 3 or 4 of them. But Bill was out there every week selling this thing, keeping the program going. between he and Paul, we needed both of them because they both brought something unique to the program. Bill had the vision. Paul said, I'm going to take that mountain. We're going to make it happen. Bill's going, okay, I'm going to be a couple mountain ranges over because that's where we're going to get to someday. They were just amazing people to be to be affiliated with, work with. Got yelled at by, it all happened. I think everyone did it one time or another, but it was just an incredible environment.
Great. Can you tell me about Paul's pizza parties, how he financed them?
Yes. If you were late to the morning, we had the morning meeting, 8 o'clock start, you must be there. You're late, you put a quarter in. And that's how we funded our pizza part. Now, I remember one morning, what was it, Dan Nolan? Who else? Anyway, I remember the guidance guy was late because he was solving a real problem that we really needed to have there. And he finally got it all together. So he walked in 10 minutes late and said, he walked in, put his quarter down and said, I got it. So it's just, that's how we funded our pizza parties was if you were late in the morning, you contributed. Absolutely. And everyone did. Didn't matter what rank you were.
Perfect.
Just a quick comment on the management style, and I am the greatest fan of Paul Clivat that you could imagine. I was so impressed. But when this thing first started, and I was a consultant to SDIO, and I lived in Southern California, so basically I was the government representative on the site most of the time because everybody else was back east. Totally without portfolio. I mean, and it didn't make any difference because we were all part of the team and worked together. But I got to admit, when I walked in there and Paul first heard that we're going to have a meeting every morning at 8 o'clock, I thought, oh crap, there goes the program. Because other places I had worked, any meeting that you started like that would probably finish at noon. Well, and you can imagine what a waste of time most of them were. Not this one. It happened, started on time. It happened quick. We got things done. Decisions were made, and you walked out the door in a very minimum amount of time. So it can work, but it requires the right kind of leadership and the concentration on getting the job done rather than going through the motions. Is what happens so many times. So I have often said this was the best managed program on which I have ever worked. And I will say that again.
Yeah, you reminded me, Jim, that because I ran that meeting second year and I got really good at, first off, looking at Paul when it's like, has the conversation gone on too long and we need to stop it? Because occasionally, well, the usual thing is if two people started talking, it was like, okay, guys, stop, take it offside, come back tomorrow. Occasionally, it was something that everyone had to hear. And I got the read from Paul, or I got to read him fairly well as far as, yes, we need to let this keep going. But it was 15, 20 minutes every morning, in, out, let's go. Occasionally a half hour, once in a while, a little bit longer because it had to be. But that was the exception, not the rule.
And my job back in Washington, D.C. was to stay out of their hair, let them run with it, and make sure the money flowed.
And you did that very well.
Yeah. Okay, well, we're going to move on to Joaquin.
Yep.
So this is where the bulk of our charts and story is on the actual DCX hardware program.
Well, I'll start by saying that this was the convergence of a number of very, very unique people that came together and enabled this happening. It was Paul, it was Bill, it was Rich Wiggar, it was Jess and your management with the vision of streamlining limited requirements and the rules that we had. And I can tell you, my 44 years of doing this is by far the highest, most rewarding, most fun program I've ever worked. With that said, let's go to the next chart. I'm looking for a better one, yet I haven't found it. Even flying X-51 wasn't as much fun as flying DCX. All right, so the whole purpose, as it was mentioned a little earlier, was to demonstrate key technologies. Okay, what were the key objectives? We wanted to demonstrate aircraft-like operations, not rocket-like operations. We wanted to fly this thing like an airplane. But obviously, we're doing this with a cryogenic engine, liquid hydrogen, liquid oxygen. The vehicle was approximately 40 feet tall. It had parts that were designed to be repairable. I get into that a little later in a little more detail. It obviously intended to be reusable from the beginning. On the right, you can see the envelope that we ended up, the flight profile that we ended up doing, but we did it in a building block approach. It was no different than flying an airplane and expanding the operating envelope of an aircraft. We went up, did a little hop, not yet, did a little hop, and then little by little extended until we did the pitch up maneuver and so on and so forth. So what came out? What was the approach? Applicable. The idea was not just to demonstrate this vehicle, but develop the technology, demonstrate the capability, so it could be applicable to multiple reusable vehicles, and some of the applications that were discussed earlier. So.
You know, that's
Again,
really important because although we kind of got tagged with the single stage to orbit nomenclature, you know, we changed the name eventually to single stage rocket technology to just highlight that the technology would support any stage, you know, whether a 1 stage or a 2 stage. It's that aircraft like operability, the high reliability, high safety aspect, which was important.
So, you know, it's hard to beat the rocket equation, and someday, and I think it definitely will happen as we work on the x-axis on weight and the y-axis on propulsion. We will get to single stage to orbit, and that will be the norm. But it's a hell of a lot easier to go in 2 stages than 1. But
Yeah.
it will happen. Maybe not in my lifetime, but it will happen. Next chart, please. All right. So it was not just a vehicle; it was a complete system. It included the vehicle as shown there, but it included a whole set of facilities and ground support system. Much more simplified than what you would find in any other launch operations in our country, or even in Europe or Asia. Basically, the vision that Pete had is we would fly these things with a vehicle and 4 trailers, and then some propellants. But it included facilities, ground support, the flight operations and control center. We had a movable hangar that also came along later on. It was kind of fun because we were out in White Sands, and Jess or someone would come out and said, "All right, put DCX in the hangar. The Russians are flying the satellite in 30 minutes," and everybody will put the thing in the hangar, and then an hour later we go back to work outside again. So again, we had some somewhat complex cryogenic engines, LOX hydrogen, RL-10s, not as complex as an SSME, but it's not your typical 327 on a Chevy. But thousands of parts that came together and operate just like an airplane. Next chart. I wanted to show some of the examples of the hardware, some of the main elements. Up in the upper right-hand corner was the aeroshell, and that fit like a glove over the vehicle. The core of the vehicle was the hydrogen stack on the center and the LOX tank. And then at the top was the avionics rack. And at the bottom, there were 4 of those RL-10A-5 engines. I'll get a little more into the engine pedigree when we get to another chart, but it was kind of along the lines of what Jeff mentioned a little earlier. It had a heat shield at the bottom. All these pieces came together like a puzzle, and they fit very, very well. And the amazing thing is we went from ATP to a first flight in 24 months, and all these things were put together and designed. A lot of the components, things like gimbal actuators and valves and like that, were borrowed by Bernie Peters, which was an old-timer that grew up on the Delta, one of the best propulsion people I've ever met from a hardware perspective. And he went all around the country borrowing parts from museums and other places that we actually ended up using DCX, which I thought was amazing. So,
Hey, Joaquin, can you describe where that LOX tank came from? And also the, wasn't that the aluminum lithium tank from?
It was the aluminum. It was the aluminum lithium
No,
tank
the
came
aluminum
from
lithium
Russia.
was on the NASA.
Ah.
Aluminum
Wasn't
lithium
the
was on
NASA?
A.
Okay.
Yep, that was A.
Yeah. And the landing gear, Joaquin, that came
Landing
from.
gear was made by the Germans.
Yep.
My buddy Gunther Langel worked on that.
Yeah.
And they
At,
came in the
Eads at
most
the time.
amazing wooden boxes.
Yeah.
Those are incredible pieces of engineering. Just the boxes that this stuff came in.
Yeah.
Was it the hydrogen tank that was coated inside in cork
No,
insulation?
balsa wood.
Balsa
We
wood.
actually had to
Balsa wood.
recreate a technology because we had to you insulate hydrogen tank, very cold, you had to insulate it. We couldn't get requalified to use 3D foam on the inside in time we got. So we brought back some retirees who insulated the original Saturn IV for upper stage. This was before the S4B, which was used on the various Apollo missions. This was a smaller prototype, but they used balsa wood. And I wish I brought my picture, but basically the inside of that tank, when they got done, looked like a parquet floor. Gorgeous, absolutely gorgeous.
Yeah.
But the
By the
reason
way,
was it could be done quickly,
Yes.
efficiently.
So my point in
and it was
starting this whole
well done.
this whole conversation was, hey, we were doing international parts and procurements way back then. It was all ITAR stuff, yet we were still able to buy stuff from almost anywhere in the world, from the communist countries to the other countries. And you know, so for those of you who are worried about ITAR, it's possible. Does require a lot of work.
So the aluminum lithium tank that was later used in DCXA came from Russia, if I recall correctly. So
Yeah.
And the upper right-hand corner, that carbon graphite air shell was made by Scale Composites, Bert Rutan and Company, which is, for those of us who like to fly, it was pretty neat. I should have introduced myself in the onset. I'm Joaquin Castro. I work for Aerojet Rocketdyne. I currently work in advanced programs at Aerojet Rocketdyne. I'm a legacy Pratt & Whitney engineer. Aerojet Rocketdyne is a compilation of Aerojet, Rocketdyne, and Pratt & Whitney, among other companies, RCA, and others. But this was at the time that we did this. This was an RL-10, and we were Pratt & Whitney at the time that we did that. Don says that the tank was lined with 3D foam from, I lost the.
From the Saturn program.
From the Saturn program. The tank was lined for 3D foams from the Saturn days. Okay.
Yeah.
All right, next chart, please. So this was also a study and execution at Treasy on procurement. Okay. As I mentioned, we went from contract award in August 1991 to a first flight just 2 short years later, so August 1993. So we're coming up to our 30th anniversary. It was a streamlined acquisition, $67 million to the first flight. I think the whole program was about $70-80 million. We rolled up these things in 18 months to a 2-year flight, as I mentioned. Things that were demonstrated in the spirit of aircraft-like operations, turnaround times, 26 hours. You know, again, and Jim mentioned why it wasn't 8 hours. Maintenance hours, less than 1,000 hours per flight, and I'll show some data on that coming up. We could just remember this was a DoD as a military vehicle. We could be on an alert and call up in 2 to 3 hours, and autonomous operation with a small crew size. Flight control, basically 2 people. Most of the flies were really there done by Pete and Ingersoll. There was 1 ground control person. We did have other people in the trailer, but we had Envision running this operationally as listed here. We had technicians, at about half a dozen to a dozen of them, and the total team was about 25-30 people. Okay, the facilities were about 600K. The whole operation and control center was less than $6 million, and the flight cost, the marginal flight cost, is about $200,000 a flight. What rocket can you fly today for that? Okay, and again, aircraft flight. We demonstrated aboard. You saw that video at the onset of the meeting. And I will never forget that. I was on headsets on the other trailer on the propulsion side, and that thing blew up because of detonation. And Peter didn't flinch. He said, okay, auto abort, press the button. Oh, we've had a problem. Auto abort, press the button. And the rest was history. The thing found a place to land. And we actually validated the fact that we didn't need an improved landing site. We were able to land on the gypsum sand of the desert. So it was an amazing, totally amazing.
So 2 questions on that. Can Jim, you give a really short story on the explosion and abort landing from inside the FOCC with Pete?
Okay. All right. Yeah. I wasn't supposed to be in the control center originally, but looking the way the things were laid out, there were 3 control screens there. Pete Conrad had one, Tom Ingersoll had the other. They were both aimed at the vehicle primarily. And then there was a 3rd one that ran the facility. They had these TV monitors in there watching the vehicle, but there was nobody watching the monitors. So I'm a very strong believer in the Mark I eyeball as a data gathering tool. So I decided I was going to stay in the control room and watch, or the trailer actually, and watch those screens, which, you know, sound like I was just trying to pad my part, but I really meant it that way. And 9 times out of 10, it wouldn't have made any difference whether I was there or not. But on flight 5, we had an excessive amount of gaseous hydrogen in the atmosphere. When the engines lit off, there was a deflagration wave through that cloud, overpressured the side of the vehicle, and blew a hole in one of those flat sides that you could see in the picture there. Now, we could never see the vehicle right after it lit off because there's a cloud of vapor and fire and dust and all like that. But as it lifted off out of that cloud, I saw, oh, there's a black blotch on the side. What the hell caused that? And then I realized that I could see through that black blotch and would see the tanks on the inside of the vehicle. It was a hole big enough for me to walk through erect, had I been there. And I quickly, nobody else saw it, obviously, because they weren't watching him. And I called out to Tom that there's a hole. I don't know what I said, but there's something wrong with the vehicle. He looked up and saw that and immediately issued a command to Pete for the auto land, which meant basically was where you told the vehicle, forget what you're doing, land immediately, wherever you are. That's the English translation. And Pete snarled at us, what are you talking about? It's flying just fine. And I said, it's falling apart. And he said, oh, and we initiated the auto land. And the vehicle came down, as Joaquin mentioned. And the beauty of landing, operating on that big flat lake bed out there is you had lots of flat spots to land in. And it made a perfect landing, but of course, landing on unprepared dirt, there was an enormous cloud of dust kicked up by those 4 engines. And the vehicle completely disappeared.
So I got
I'm
one
sitting
more.
there feeling sick at my stomach, looking at that, looking at that cloud of dust. That's it. It's gone. It's gone. And then I saw the little bitty tip of its nose sticking out of the top of the dust cloud, which meant it was still vertical. And I have never felt such a sense of relief in my life. Well, maybe once or twice, but that was a real sensation that maybe we were going to make it. And sure enough, the vehicle was badly damaged structurally, but it flew and it landed and it did exactly what it was supposed to. And that alone made me an even bigger believer in the powered vertical landing, because had that been an aerodynamic vehicle dependent upon aerodynamic lift, particularly on wings, they would have been gone after that explosion, and there's no way we could have salvaged it. So
Okay, we need to move on.
Really,
let me go ahead, Jim. So we did get a note from Greg Mahalik, Aerospace Corporation, said that the entire abort landing was Jay Penn's fault at the Aerospace Corporation. So, but aside from that, Joaquin,
he's standing over there, or sitting over there.
okay, Joaquin,
well, anyway, that was my story as far as Flight 5 is concerned, but I was sure glad I was there.
Joaquin, can you talk a little bit about Dan Golden? Because normally you don't want your boss at this kind of an event, but I think he was there, and he saw the big holes in the gypsum. Were you there when he was?
Well, no, but I wanted to make a comment about Dan Golden. We were not just hoodlums; we were sand hoodlums.
All right,
according
go
to
ahead,
Dan.
Let me interrupt. Jess, I think you're remembering one of the landings we did on A, where we had to fill the holes in before Golden got down there. Dan Golden on this flight was sitting in a meeting in St. Louis. Reuters ran in and told him that the vehicle was destroyed, and I had lots of explaining to do.
Okay.
All right. There was a question on the chat. Let me address that. Somebody says, how do you get water out of the engines if you're running cryogenic propellants? Well, it's very simple. This is an expander cycle engine. This is not a stage combustion. This is not a GG. There is no water in the system. There's no products of combustion in the internals of the engine. So the way we had this engine designed, there was only one place in the engine that I had to drive was the GOX valve, or which we use for ignition only. And I already had a design in place that I had to remove that. Other than that, on an expander cycle, there is no need to drive the engine. And again, it took 2 hours to drive that GOX valve. And we said it took 2 hours to get the engine ready for flight. And in the meantime, I went out and we checked the igniters and we kicked the landing gears and whatnot, just to do something while the thing was drying. But there's no need to dry an expander cycle. I do want to take a moment, just because I think it's important for everybody to understand. We talk about the deflagration of the detonation of the engine. Back when we were doing the static testing in White Sands test facility, we learned that we needed to have the wind blow that hydrogen to minimize the deflagration. Deflagration was not a problem. What happened on flight 5 is we had a fan with an inlet about 50 feet from the launch pad that blow air to dissipate the cool down LOX that was injected through the injector. The RL10s have to be injected. The hydrogen cloud comes from the hydrogen cooling the hydrogen part of the engine. LOX was flown through to the LOX part, and it just went through the injectors and out to the ground. And that fan was intended to dissipate that LOX. We had a concentration of LOX. The wind had shifted and blew the hydrogen cloud into the inlet of the fan about 50 feet away. Maybe it's more than 50 feet. I can't remember. And that mixture of hydrogen and air was caught in that long pipe that brought the air to the bottom of the vehicle. That is what created the detonation wave. And had we not had it, and it came out through the dock and upward as the vehicle launched. And it was because of that we had the accident, because it was a detonation. The normal deflagration was never a problem on the vehicle. So I don't know if you guys remember those details, but I remember vividly because I had to work through all of that. So
Okay, you got about 10 minutes left. So
next chart.
get into it.
All right, so 12 flights, 8 DCX flights, 9 DCX, 8 flights. I am going to go to the next chart to talk about some of the details. You can see some of the elapsed times between flights and whatnot. Next chart. I think it's a little more meaningful with a lot more pictorial. Program started in 1990. We were awarded a contract in August, September of 1991. The rollout, which is the picture that you saw that Jeff showed earlier, was in early 1993. The first captive test shown there in June of 93. Then flight 1, April to June. That was over in White Sands. Flight 1, 18 August of 1993. That's the birth of our vehicle. Okay. First 3 flights were good. On the third flight, we have an anomaly at liftoff. What basically happened is we were using helium to cool down the LOX line, and one of the RL10 engines ingested some of the helium. Well, helium is not just like LOX, and the engine basically lost thrust. Because the RL10 has a gear set of turbo machinery, there's a single turbo pump for the fuel side, and there's a gear that powers the LOX pump. Those two are connected together. Because of the fact they're geared together, even though the LOX pump cavitated and it affected the ignition and the chamber pressure on the engine did not run away. Had that been an engine where the 2 pumps were not locked together, it probably would have bursted and created a class 1 accident. But because of the design of the RL10 and the way it was done, basically we had one engine that lost power, the vehicle climbed and then tilted to a side, and within about a second or two recovered, and we continued the flight. But then we went down anyways, and we're down for a while until we investigated and determined what would happen. That was followed about 9 months later by flight 4, when we first loaded the tanks for the first time. Flight 5 was the abort that we've been talking about. I'm not going to dwell, that's been discussed. And then flight 6 did all the propulsive controls. Now we're into 1994, 95. And then it was a building block approach. Remember, we started with a partial rotation maneuver in June of 95, and our final flight 8 full rotation maneuver was in July of 1995. And then we had to stop because we ran out of money. We got a new president in the White House, and BMDO couldn't give us any more money. And then we got Dan and Dan to save us from NASA. Okay. And then
Hey, Joaquin,
yes.
forgot that on flight 8, we had the little radar problem. You remember that one?
No, I don't.
Okay. When we did full rotation, it was the first time that the radar lost lock on Earth because we did left for rotation. And just being 95, we had a variety of things to figure out where we were. We had onboard system, we had our onboard navigation, inertial navigation system, we had the beginnings of GPS, remember that? And we had a split radar to figure out how far above the ground. The problem was it was all mixed together in the guidance. So as it was climbing out, and then we did, as we get above 5,000 feet, the radar kind of lost lock on the ground. We knew that would happen. But what we didn't know is the radar could, shall we say, send false signals into the system. So it thinks that we're at 5,000, 5,100, 5,200, and then it goes 4,000, 3,500 and stops. So that gets locked, that gets into the computer credits, adds that all together. So the rocket now thinks I'm below where I'm supposed to be because an average is allowed. So it accelerates its rotation altitude. It does the rotation much higher and faster than it was supposed to, comes back down, it's coming back down. It thinks it's about 4,500, 4,000 feet. When the radar kicks back in and says, no, you're now at 5,200 feet. But it doesn't take that right away. So it's adding and subtracting and blending all this stuff. So it thinks it's behind. It thinks so it throttles back and descends faster. And the error is slowly working its way out. And as I was told, at about 100 feet off the deck, for the first and only time, all 4 engines were commanded to 100% throttle. Bill Reed here's inside the landing gear. There was these 4 canister shock absorbers to take a little extra load. And each flight they'd crush a little bit. They'd crush a little bit. If you had brought that pad, you would see this nice 18. I think it was 18 inches crushed down to about 1 inch. Yeah. It took it, and then we declared victory at that point. We're going to shut down for DCX. But that was a fun flight.
On the interest of time, I know Dan is going to cover DCXA, so I'm not going to go. There were 4 flights, including the short turnaround, and then the last flight, the tip over landing. But I know Dan will cover those. Let me next chart, please. All right, this one basically shows the people hours per maintenance, and the fact that when we didn't have any anomalies or things like that, with that under 1,000 maintenance hours between flights, which was excellent performance for a one-of-a-kind experimental vehicle. Next chart. So from what were we trying to do? We were trying to improve reliability, maintainability, and supportability. Pretty much every component on the vehicle was designed in order to be able to do that. We had readily access to all the components, all the way from the avionics to the engines. We could get in there and do that. And all, as I mentioned earlier, all the technology was intended to be traceable to demonstrate its applicability to other reusable vehicles. However, from a lessons learned, the thing that I have encircled here in red is the one thing that I want you to take away. You know, as important the one above, that, you know, most of the life cycle cost savings are done in the concept. When you design, you don't want to be fixing things, you want to design them right. And reusability has to be designed into a system. You don't take an expendable rocket and put legs on it and flaps and say it's reusable. Now, that's the hard way of doing things. But the one thing I want you to take away is aircraft-like operations and maintenance systems are compatible with operating rockets, RLVs. We demonstrated that in spades. And that, to me, is the big contribution of this program that, as just mentioned, is the father or the mother, whatever gender you want to pick, of the reusable vehicle system in our country and the rest of the world at the time.
We also had one question about the conical tip. Why go with the conical tip? And I'll just say that in this era, when we were first flying this, there was a ton of data on RV-shaped reentry vehicles. So aerodynamic data across every Mach number. So when McDonnell Douglas put this together, they borrowed from that huge aerodynamic database, and they ended up with the conical configuration, as opposed to what you see with SpaceX today, where it's more of a cylindrical configuration. but they both work.
Next chart. All right, so obviously I'm biased. I'm a propulsion guy. You can see what I said there on the model, the business end of the vehicle. 4 RL10 8-5 engines, 13,000 pounds of thrust down to 3,000. There were the turbo machinery and most of the valves were from an RL10A 3.8 engine. We were the first ones, to my knowledge, to employ electromechanical actuators in a hard cryogen engine. There were three major modifications that were made to this engine. Number one, we took the RL10 thrust chamber, which is at the time was like an 81-to-1 area ratio chamber, designed for in-space operation, and we made it a sea level operation. I think it was like 6-to-1, or I can't remember it right now, the area ratio in this. And it was a totally new thrust chamber. The second one was the addition of EMAs, electromechanical actuators, to both the thrust control valve, which is the one there in the upper right hand of the engine, and the oxidizer flow control valve. The RL10 has the ability to change mixture ratio with operation. And as we throttle up and down, you could imagine we have to change not only the thrust command to the engine, but also the propellant, the fuel oxidizer ratio in order to keep things in order or in proper balance. The way the RL10 works is that thrust control valve controls the hydrogen bypass that's been expanded through the chamber and decides how much of that goes into the turbine, how much of that gets bypassed around. And by doing that, it controls pump speed by controlling turbine speed. And by doing that, it controls chamber pressure and hence thrust. That's the quickest I can tell that story. Next chart. So a little more detail. I mentioned there were three things. I mentioned the chamber. I mentioned the actuators. The fuel control valve, or the thrust control valve, is that thing that's sticking out on the right side, sticking out at a 45-degree angle. That's the EMA that attaches to the thrust control. And you can see the bypass section there on the turbine housing with a little tube sticking out, bypassing the flow when you want to reduce the pump speed. There's a similar EMA behind that big cylindrical piece on the oxidizer flow control valve. All the other valves in the RL10 are pneumatic. The third thing that was probably the most difficult, believe it or not, is the RL10 is an in-space engine, and it has a significant amount of efflux in space, not significant, but it's got some leakage in space of the hydrogen and oxygen. Flying inside the atmosphere at sea level or at 3,000 feet at Y-sand, we could not allow any hydrogen to come out. So that big tube was called a collector manifold, and that basically collected all the different flows of hydrogen from the engine and pipe it to a pipe that went out to the side of the vehicle and was ejected. It's what you've seen in the films and some of the pictures. So those were the three major changes: chamber, the ability to throttle by putting EMAs on the oxidizer flow control valve and the thrust control valve, and that collector manifold to make sure that we could operate in an oxygen air environment. Again, just in summer, the RL10 8-5, 4 of them power the vehicle. Full thrust was 13,000 pounds. We had 3-to-1 throttling down to about 3K, mixture ratio 5-to-6, and the engine only weighed about 315 pounds. So it's a beautiful engine, and it did a fantastic job. And we went from nothing to running our first test engine in the test stand 11 months. And we delivered 4 flight clear engines that were not certified, that were not sold, not DD250s, that were loaned to the program in 18 months. Nothing to a first engine test in 11 months, 4 flight clear engines delivered in 18 months. Whoever tells you it can't be done is because they're putting up with too much red tape. It can be done. And at the question and answer sessions, I'll be happy to tell some more stories, but just next chart for now. So any of you to go to New Mexico, the engine 502, which is the engine in the picture, is on display at the New Mexican Museum of Space History as part of the DCX exhibit in Alamogordo. That I show you the performance of the engine. That engine accumulated a total of almost 3,353 seconds, 1,200 and almost 50 seconds of flight time. And static firing is about 190 seconds, and engine ground test time almost 2,000 seconds in Florida. And all 4 engines pretty much have between 30 3,200 and 3,800 seconds of run time. So, you know, we demonstrated reusability 30 years ago on an RL-10. Okay. Total firings over 35, 12 flights, 9 vehicle static firings, 14 ground tests. And again, like someone said, we didn't think this was work. We were excited about the program. At the time, we had plans to take a DCY, which would have been the next evolution, and land on the moon. I had to chase my people out because if we were going to test in second shift, they didn't want to go home, even though they work all first shift. Everybody was so excited and enamored with the fact that we were changing the way we were going to go to space. And it was a privilege, and it was exciting, and it was again, in my career, the most rewarding program I've ever worked. Next chart. So I'm going to read the blue ones because I'm running out of time. So this came out for Jess and the people at the government. We need to clearly define program objectives in advance. One head in the snake, single manager under one agency, not all these multi-agency things like we did in other programs. Built hardware, not paper. Streamlined documentation and reviews. Requirements in the RFP were 2 pages, not a 200-page RFP like you see in some of our programs today. And the team, we trusted each other. Once we came together, I was from Pratt & Whitney, you know, Jess was from the government, and so was Jim. McDonnell Douglas, all our badges went in the pocket. We were one team. We were one family. To the point that today, 30 years later, we still have a kindship for each other because of the experiences that we share. Next chart. And by the way, we deliver on schedule and budget. There were plans. Jess, I think you probably briefed this better than me because you have more insight on the plans than I did as to where we're going with this.
Yeah, I mean, we were, McDonnell Douglas, I should say, was really looking to how they could take DCX and turn it into a capability. And they had a proposal together for X-34, which would have been to build a Mach 8 aircraft and go fly, as well as what became Venture Star. So unfortunately, neither one of them happened. They didn't win either one of those awards. So the one for the X-34 was about $100 million program. And, you know, the world would have been different had we gone and take that, because 80–90% of the hardware was identical. You could have just moved on and gone and built a follow-on demonstration vehicle for X-34.
So the propulsion perspective was going to be one SSME in the middle surrounded by RL-10s, as I recall. So
yeah, I think it was a Russian LOX hydrogen engine, but you know, one SSME would have been better yet.
Next chart. This might be my last chart. I'm not sure. Oh, and this one, I take somewhat responsibility. We had our first flight. This was August 18th, 1993, and it was ominous. The storms were going to break. It was lightning. And I said, but we can't go away. We got to take a group picture. So I kind of harass everybody, and we got into a good picture. The guy on the fatigues in the middle is Jess. You can see Pete Contract there with a beige jacket and the hat on the right. The guy with the blue suit and the blue hat is myself. Don, there you are on the left, just next to Jim Holloway with the blue pants and the light shirt. There's Don. So unfortunately, we have lost a lot of these folks. I kid you not, guys, it's the best team I've ever worked with. It was a privilege and a pleasure to work with those of you who are still here, with those that are gone.
Yeah, and I want to point out that as the lightning came down and struck the gypsum back behind there, and after this photo, 90% of that crowd hightailed out there as fast as they could go. But there were about a half a dozen of us who stayed around, and we had to erect with a cherry picker a catenary lines. We had 4 lines coming down, and they were out. The guys were out there with sledgehammers, hammering these catenary lines into the ground because we didn't have time to put the vehicle back in the shelter. We had to leave it out there in the monsoon thunderstorm. So I'm sitting there watching these strikes on the desert back behind it, getting closer and closer and closer. And I'm saying, hurry up, hurry up. So at any rate, it was it's not what I would, if I would have been at Vandenberg or the Cape, they would have court-martialed my ass. But, you know, out here, we were allowed to do things differently. And yeah, there was a little bit of risk involved, but it was prudent risk.
Well, Jess, I remember when after the first tanking at White Sands during the static testing, we wanted to make sure there were no leaks. And 3 of us were commissioned to go into a fully propellant loaded vehicle into the boat tail. We had a safety guy with a nitrogen and hydrogen detector ahead of us. And it was me, and I wasn't Jerry. I can't remember who the other person was. And we actually went inside a fully propellant loaded vehicle, which is a no-no today,
Yeah.
and did a visual inspection of a fully fueled vehicle at the ground test site. Next chart. Well, first successful ROV plane, and again, is a genesis of some of this work. Aircraft-like operations is still valid. That's what we need to do. We don't need to do rocket-like operations. We need to do aircraft-like operations, and is needed. And the DCX operability demos still lead the way into the ops and really show the way to make that happen. We never went to orbit. We didn't need to. It was an operability demo. It proved all the systems that were required to do that and the operability of it. And is a roadmap for the future, as we've discussed. And next chart. I think this is my last chart.
Yeah.
Dan,
so,
over to you, DCXA.
Dan, we're about 10 minutes behind schedule, but we got lots of margin in the schedule, so you're good.
Am I, do you hear me? Did I cut in?
Go ahead, Don, you're on.
I just, quick, when we were given those engines, they were told us they wanted them back. So we designed that structure like the Mercedes front end. So we had a core of the vehicle, but the shell carried the landing gear. And so when we had that explosion and the thing landed, we took all the load off the core, and it was all in the shell. And later on, I've been challenged many times on why that happened, but it was the design that actually what Joaquin wanted his engines back, so we did every good thing we could to get them.
Thank you, Don. And because of that, people can still see that engine in the New Mexico Museum if they choose to. And the other 3, last I checked, are sitting in a warehouse here in West Palm Beach.
All right, so now we're going to switch to the phase where NASA got involved, and a couple of points I want to make before I get too far down the road. Number one, Joaquin had a chart a little while ago that showed a contract awarded. Actually, it was not a contract. It was a cooperative agreement. And it was the precursor of what became the Space Act agreement that put COTS in place for commercial cargo and crew. And so that was actually, that procurement mechanism was actually first tested on XA. It also was used on X-33 with some new constraints that actually added to the problem. But that's one of the things that NASA did early on in this was to make sure that we did it, the commercial, we did the procurement in a new way, which actually, one of the things I want to say, I want to say publicly, thank you to Jess, thank you to Jim, thank you to Jeff, thank you to Joaquin, because they set in place one heck of a foundation. Everything you've heard on how the program was run internal to McDonnell Douglas, how we did the operations, the daily meetings, all of that was applied on the NASA side of the equation. We did not change that. In fact, the one thing we did do, in addition to having Jim French there almost every day, is we actually moved a NASA structural engineer on site working with McDonnell Douglas that was part of the program. So we worked very hard to live with the rapid technology demonstrator, the rapid prototyping mentality that you've seen the foundation set for already. If you go to the next slide, please, Ken. One of the things, I'll just step through a little bit of this. NASA did DCXA as part of what was called at the time the Reusable Launch Vehicle Technology Program. Some of you may remember our good friend Gene Austin and others that were working on getting this RLV technology together. And actually, Gary Payton had come over to NASA about this time to be part of this. So he went from the SDIO arena. Mike Griffin was over at NASA as well. So there was continuity from that perspective. And what was driving what NASA was after was the recognition or the potential that the satellite communication growth would be so much, the growth would be so large that it would, that reducing the launch vehicle cost actually provided a commercial business case. It turned out in the long run that terrestrial landline or terrestrial cell phones beat the satellite phones to the market. And so the business case kind of disappeared on us. But what we did with DCXA was primarily focused on developing some new technologies, taking advantage of what Jess and company had done on the DCX project, and then go off and do the flight test. When I first got involved in the program, NASA had just completed a study as to the applicability of DCX and what became XA to the Reusable Launch Vehicle Technology program. Dan Golden was the administrator. And that study came out and said that it was going to be a good thing to go use and build upon the DCX project and create the DCXA flight test demonstrator and continue that on in the RLV program. We utilized all the streamlined management approaches. There were 2 of us in the project office, no more than that. We had about 10 people working the engineering across the board, had the on-site structural engineer. And in terms of streamlined management approaches, I will highlight that the flight readiness review that I had to go through on the NASA side was a 2-paragraph email to my center director. And that was it. This last bullet on this slide, I like to highlight anywhere and everywhere I can, because the team that you've seen already, along with the team that continued through XA, met all the flight test objectives, did it on schedule, 2 years. And I had the honor of calling NASA headquarters up and saying, what would you like to do with this extra money that I have? And Gary Payton said, hold on, Dan, let me get back to you. We weren't expecting that phone call. But we actually did it, 10% under budget. We did have plans to continue off on that. Gary and Dan Golden had us looking at potential plans to take XA and do additional work with it. Unfortunately, the last flight test took care of that problem for us. If you go to the next slide, please, Ken. There we go. No, one more. Go back. There we go. So the technologies that we put on XA, I'm going to step around this a little bit because there were some new technologies here that were new to the launch vehicle industry. We had new thermal protection systems that were coming out from the Ames Research Center and other places. We were updating the avionics to the aircraft level. Jess already highlighted that the liquid oxygen tank for DCXA was aluminum lithium. It was built by the Russians under contract to McDonnell Douglas. And it was also an aluminum lithium tank that flew before aluminum lithium was used on the shuttle program. So this was actually the first aluminum lithium tank to see flight environments. We did some hot structures work. We tested those out on the heat shield, lots of graphite epoxy structure. We took out the metallic structure that was used on X and designed that with composites to demonstrate composites use on a launch vehicle in the flight environments. And then in addition to that, and this was the big technology item on XA, was the graphite composite liquid hydrogen tank. We also did a valve and a feed line. The hydrogen tank was the important part. And Don Steinmeier has already pointed out that the X tank used internal insulation. We used that same internal insulation on the liquid hydrogen tank for DCXA. And as I recall, I don't have the numbers directly, but as I recall, we put over 50 fill and drain cycles on this hydrogen tank. It never leaked, and it only leaked after 2 minutes worth of sitting in the heat after our little incident on flight 4. So we did one hell of a proof test on that tank. And as Wayne Littles, the center director at Marshall Space Flight Center, told me one day, great proof test, Dan, don't do it again. And unfortunately, we didn't have the opportunity to do it again. We did have some auxiliary power systems on board, and that's part also where we used some of the composite valve and feed line. And we were going to work a main propulsion power head demonstration. We ultimately had to set that aside just because of timing and money. The cooperative agreement we used on XA did allow us to change and add scope, but there had to be a contribution, so to speak, either in kind or dollars from McDonnell Douglas. That was the nature of the cooperative agreement. So we were very, very careful about assuring we maintained the requirements, didn't change the requirements, and only added scope where absolutely necessary. So let's see, Ken, can you go to the next one, please? So some lessons learned, and I'm not going to go back through all of it. You're going to hear a lot of the same thing, but again, just a reminder, we manage this program DCXA based off the model that you've heard described for DCX. We had the same daily meetings. I actually remember them being at 7:45, Jeff. Pacific. But again, all the right people were on the phone. Everybody was involved from the operations side all the way through the design and development. Everybody was there. We made sure we had stable requirements and stable interfaces. We had to be very careful with the interfaces by bringing all these technology items together. Joaquin highlighted trusting the people. That is absolutely the case. And we worked very hard to retain that same team camaraderie and trusting of the people. We recognized that we had to take some risk, and we worked to accept the appropriate risk. I will highlight one quick thing. My good friend I notice online is Dan Nolan. And Dan's wonderful analysis and GN&C capability for X and XA allowed us to continue flight test when we ran into some issues, when we landed on the grate for the first time, then tried to land on the sand. And that didn't work too well, particularly when Dan Golden came up there. And I know on his way up, I know the guys were busy shoveling some gypsum back underneath a couple of the landing pads, so it didn't look so bad, even though we were stable. We did plan in budget and schedule margin. We were careful to do that. Schedule turned out fine. Budget, we actually underran, as I highlighted earlier. We had the flexible acquisition strategy because the cooperative agreement did allow us to move things around a little bit. And one of the things that was really clear in all of this, and it's a theme that runs through everything you've heard tonight, is this team was willing to identify and test all of our assumptions. We were willing to question each other, did it very professionally, sometimes not so professionally, but always with the best intent. And this team did a tremendous job, and all the lessons you've heard learned from X apply to XA, and the new technology lessons that we learned, where composite hydrogen tanks or composite propellant tanks are now being considered more and more, and you see more composite structure being used, and much of that can be traced back to the work done for X and XA. If you go to the next chart, please, Ken. So in summary, we did demonstrate the aircraft-like operations. I talked about the flight test objectives. I will highlight that aircraft-like operations, Joaquin mentioned it, and Jim's mentioned it as well. On flight 11, between flights 10 and 11, we had the goal of doing the turnaround in 8 hours. Unfortunately, we were ready to go on between flights 10 and 11 until the thunderstorms came rolling in across the mountain range on us, just as we were getting ready to load propellant. So we had to stop. And as it turned out, we were on White Sands Missile Range, and the Army had priority for a program the next day. And the range could not get to us until the afternoon of the following day, thus the 26 hours. So we demonstrated the 8 hours, similar to what Jim described. I will also tell you that Pete Conrad comes up to me after flight 11, and he looks at me and he says, 4 hours, Dan, 4 hours. And I very politely, in some rather colorful language, told him, no, thank you. Enough is enough. We demonstrated the management model. Everything you see with DC from a NASA perspective, it was a great experience for demonstrating the technologies, demonstrating how to manage a program, demonstrating that you could do it quick and efficient. And it set the stage for what ultimately became the procurement instruments and the approaches used for commercial cargo and crew that we now see the business base building for space station and then evolving into other commercial operations. And I like to think, and I will let Jim and others be the judge of this, I like to think that a lot of what we learned here from the vertical landing perspective and how to do these programs efficiently, because of the members of the team that went on to work at SpaceX and Blue Origin and other places, has more than returned its investment to the industry, because of all that learning accomplished across the workforce, then found its way into commercial application, and DCX and XA exhibit provided that foundation.
Hey,
So,
Dan,
yeah, Jess.
I got to add that I personally had Elon call me when I was at DARPA and asked for all of our DCX and XA data, which I sent to him, about 5 gigabits. And Rob Meyerson at Blue Origin also had collected some of the data. I'd collected some, and we put together the complete package. So we gave the data, certainly to those two companies, and I distributed that data to at least another half dozen US companies that were interested in reusable operations.
Yep.
So it got out there.
Exactly what the taxpayer investment should do.
Yeah.
If you'll go to the next slide, the next 2 slides, and I'm not going to step through them because they're kind of detail oriented and we're a little bit behind time, but they're there in the package, and Ken has it and can distribute it. Give you a few more important accomplishments at a little bit finer resolution for X and XA. This slide and slide 39 can give you additional input. And then with that, I think what we'll do is the next part of this was to have Jim, if he doesn't mind, talk about how he sees things and what we learned from this, and how the DCX and XA technology has lived on. So Jim, I will turn it over to you and then add NASA color commentary as appropriate.
Okay. Okay, I've got a couple, I'm sorry. A couple of slides to talk about, but the bottom line was that when the program got canceled, when there was no longer going to be an SSTO, when the follow-on programs X34 and X33 went pretty much down the tubes, I got to thinking about how we could salvage some of the ideas, not so much just the technology, but the ideas, the concepts of rapid turnaround and that sort of thing. So I was still a consultant, just not working for anybody in particular. So do we have those other slides?
Hey, Ken, you're gonna have to go back towards the beginning where they were.
Yeah, they were up in your section in the earlier part.
Anyway, I got to thinking through the problem and how we could do something inexpensively to still maybe take advantage of.
Right there.
That was it. You went right by them. Yeah.
There you go.
To how could we take advantage of this technology that we've demonstrated and do it even more cheaply? And one of the problems that you run into with a single stage to orbit, like we were pursuing for SDIO, was that no matter how good you are, with the limitations of propellant and the rocket equation being what it is, you can't get as good a payload fraction as you would like. No, for a given takeoff mass, you're going to have a relatively poor payload fraction for a single stage orbit vehicle. So I got to thinking, well, why can't we do this in a fashion that takes advantage of most of the kind of thinking we were doing, but we can do it inexpensively and take advantage of these concepts and get some inexpensive, reusable, relatively inexpensive, reusable vehicles online. The stuff that we could fly and bring back and fly again. And so the bottom line was, after noodling about this up for a long time, go to the other slide first. No, not that one, the other, that one. This is possibly the ugliest thing that I ever designed, but I was trying to, first place I was trying to think, what could we do without having to develop any new engine hardware? As we know, developing engines costs money and takes a long time. So I thought, where could we go with hardware that we already had, like say RL10s and RS27s, the Thor or Delta main engine. So basically, I came up with the idea of a two-stage vehicle, where the first stage contributed only a very small amount of the total energy. What it did was it lifted, what I called it, it's an oxymoronic name, but boosted single stage to orbit. The idea being that you take a single stage to orbit vehicle and lift it up to a fairly high altitude and a fairly good velocity, and that thereby improving substantially your payload fraction for a given size vehicle. But you have a booster underneath it that gets it there, but the velocities involved and the distance involved is such that the booster can either land close enough that bringing it back on a truck is a viable option, or I was thinking of landing on land, not going out in the ocean. Or it could fly back and land. Now, and that was the concept. And I thought, what's the simplest, stupidest thing I could put together using those concepts? And there you see it. the boosted single stage to orbit concept with if I remember correctly, there were 8 RL-10s in the upper stage and a much more compact booster under it that had 3 RS-27s. Now, one of the concepts that I thought was viable was that I thought we needed to be able to stay in orbit for a lengthy period of time as the shuttle does. And you remember the time period we were talking about, keeping liquid oxygen, liquid hydrogen, liquid in orbit for a period of days to weeks was pretty much an unheard of idea. So I figured rather than do that, I'll just play the penalty and carry some storable propulsion for on-orbit maneuvering, deorbit, and landing. And both vehicles, the booster and the stage, would have the clusters of the same landing engines to be used for the purpose I just described. So this is not proposed necessarily to be something that would ever fly looking like this, but this was a first cut at how you had put together all the pieces and parts that you needed. And basically we have something here that could be a human carrying vehicle with 5,000 or 6,000 pounds of payload to low Earth orbit, where the booster would either land a couple of 100 miles downrange and be brought home, or conceivably fly back and land at the launch site, which is my preferred mode of operation. The vehicle on top, if you remember the Gemini program, this is basically a considerably staged up Gemini with LOX hydrogen propellants, 8 engines, and a payload volume on top, which could carry a human crew capsule or could carry cargo to orbit. So this was kind of a cut I made at where we might go with the kinds of ideas we were talking about for rapid turnaround and that sort of thing. So I was doing this on my own. Nobody paid me for it. And that's why it's so ugly. You get what you pay for. But it didn't go anyplace except into my files.
I
2000 or 2001, I got a call from a person of whom I'd never heard. And he said he had found my name through the usual mutual contact type of thing from a guy I'd worked with a lot at JPL. And he said, quote, "I represent this very well-to-do individual who wants to invest some money in reducing the cost of space travel." I said, "Well, I'm all for that." And so bottom line is he offered me a consulting task to do that, to put together some concepts that might be something that this rich person would want to be involved in. So I did that. My first approach was that to try to do some advancements in propulsion that would make the payload fraction a little better, so we could still stick with the single stage to orbit concept. So I put together got several people that were working on that sort of concept, put together to make a presentation to the person who was going to fund this. And at the end of my conversation with the gentleman who first contacted me, I said, "By the way, who is it that is providing the funds to do this?" And this will show you how I was really on to all the hot trends of the time. His response was, "Jeff Bezos." And my response was, "Who?" That was back in the days before he became a household name. And I had heard of Amazon because they were putting on some ridiculous radio ads in those days about Amazon, but that was the extent of my knowledge. Well, anyway, we had a presentation for Jeff of the ideas that these individuals that I'd rounded up wanted to present. And with one exception, he didn't like any of them. He did like one a little bit and funded the guy for about 6 months and then dropped him. So I said, well, since you don't like any of that, how about I make a proposal to you based on the concept that I came up with out of the single stage to orbit program. Okay, fine. So I went and dug this out of the files and put together about a 5-page proposal about how I would think we would approach developing this vehicle to provide low-cost space transportation. And took that to Jeff, and he said, okay, that looks interesting. And right there, he contracted me for a $50,000 task to bring together a group of engineers and do a relatively detailed study of this concept, in essence, doing a real proposal. So we did that and came up with about, I think it was about 50 pages or thereabouts, details of this concept, wrote it back to Jeff. And this will sound like a made up story, but is the honest truth. We all sat there quietly while he read through it. He finished it, closed it up, put it on the table and said, okay, that's what we're going to do. And I was stunned. But from that point forward, Blue Origin, which prior to that had consisted of a couple of guys sitting around an empty warehouse in South Seattle, became a company. And we started hiring people and started working on a concept basically like this. Now, as anybody that's been in engineering business knows, when you get to the end of the program, what you wind up with doesn't look anything like what you proposed at the beginning. And for any number of reasons, fairly early on, this went by the wayside. We went into a different direction. Part of the problem was that when I proposed this, it was based on some conversations we'd had with what was then Pratt and Whitney and Rocketdyne as separate companies. And they offered some very reasonable prices for both the RL-10 and the RS-27. So we, that made it kind of sound feasible. Well, when we tried to investigate it again from the Blue Origin viewpoint, the prices were no longer reasonable. So nor was the schedule. So we figured we would have to develop our own engine, and that changed a couple of other things. And so the bottom line is this vehicle, it served its purpose of carrying the idea forward from the single stage to orbit program into one of the new companies, Blue Origin. And that's what led us to where we are today with the vehicles, the New Shepard vehicle and the new Glenn vehicles and a couple of rocket engines that Blue has developed. So now how Elon Musk and SpaceX fastened onto the idea, I don't know, except that I think this basic idea is a very good idea for trying to do low-cost space transportation without pushing you to the extremes of single stage to orbit. And so Elon and the people that work for him are not stupid. They recognize a good idea when they see one. And I think that is, they've basically followed a different logic path, but came to pretty much the same conclusion as this was based on. So that's my 2 bits worth on how we carried on from single stage to orbit program into what's going on today.
And if I may jump in here, just extend, and I mentioned it before, DCXA from a NASA perspective then morphed into X-33, and that was a competition that turned out the way it did. And a lot of the technology transferred over, and you now start to see it showing up in different places on a line item level. The important part is the procurement mechanisms, and some of that have followed and provided a foundation for the future. I will say, though, that in Dan's humble opinion, it could have been done better on the NASA side. I think we sometimes get a little bit too bureaucratic. So, but I think if you stand back, just from a quick look, you see Jim and and how it flowed into Blue Origin and other things. You can still see parts of how DCX and XA helped train a few people and help provide a basis for a future that hopefully we'll get to sooner rather than later, and we will, hopefully the next generation comes about and learns from this. One of the things I like to tell the young people about X and XA is be willing to question and be willing to ask why and why not. I came to this from a shuttle program where free venting hydrogen was verboten to a application where it was actually okay. Now, we may have decided to do something differently if we had more time, as Jess pointed out earlier, but it was okay to do it in this environment. It was not okay to do it in a shuttle environment with people on top. So you have to be willing to question your assumptions and think things through. And I always like to tell the young people in the next generation that that's one of the key lessons that should come out of this. Jess, anything you want to add?
Yeah, one, I just want to point out that when DCX flew, we had a tremendous amount of national press everywhere. And NASA came into the program. Dan Golden got interested. So there was about $2 billion, maybe more, that was eventually invested by NASA trying to solve the reusable launch problem and the shuttle next gen solution. It didn't work out, but a lot of technology and concepts came out of that. And then at the same time, there were a lot of, there's really been 3 generations of children of DCX. The first was people like Kistler and Rocket Plane and several others who came in the 1990s and tried to make a commercial reusable launch system. I call them the barnstormers because they all ended up flying into the sides of barns and going bankrupt. Then we came to the billionaires. And so that was Elon Musk coming to the table, Jeff Bezos coming to the table, and also Virgin Galactic. And so that was around 2000-ish where all of those came in and started investing heavily. And then most recently in the 2016, 17, 18 timeframe, I call the third generation the investors. And those are Relativity Space, Stokes, Rocket Lab out of New Zealand. So we've got a lot of people pressing down the path of reusable launch systems. And I consider all of them to be the children of DCX, and all of them that I could give the DCX data to, I did. So I did want to mention that the Air Force interest here has always been for many years, as I showed in that chart earlier, this idea of a global reach aircraft capability that can do a lot of different things. And I mean, responsive launch, the ability to rapidly deploy assets that are lost and replenish them as required. The Brilliant Pebbles deployment concept was already discussed. You can kind of modernize that to what Elon is actually doing with this commercial Starlink constellation. The other important mission the Air Force was interested in was information surveillance reconnaissance, being able to be anywhere in the world quickly with nobody knowing you're going to be there and to be able to look at things. And we've done a lot of work since then on global reach weapons called boost glide weapons. The Chinese actually flew last year something called a fractional orbital bombardment. At least that's what it was called in the press. That's not really what it was. It was a boost glide weapon. But they flew it all the way around the earth and came down and impacted on the Chinese test range. So there's a lot going on in all of those things, and you can actually put these things together and have a way to launch all that kind of stuff and provide a capability anywhere in the world. And all those are still valid military concepts that will be important to the future. But I like the current thrust of what's going on in the commercial sector. Let the commercial sector lead the way, and we'll figure out how to do all that But watch your back because the Chinese are moving really fast down this path. Far faster than the US government is.
Yeah, very true. So Ken, I think with that, we probably got about 5 minutes for a couple of questions. If anybody wants to, we've been answering questions along the way, so that's good in the chat and other things. If there are any other questions anybody wants to bring up, now would be a great time.
Yes, Ransomberg. It's not really a question, just a quick comment. There's a name that I didn't hear today, but I think it's important. That's Max Hunter.
I mentioned him.
Sorry,
Yeah,
I missed it.
Yeah, he was involved early on in the origins of the program. Had dinner with him many times. He was a great visionary engineer out of McDonnell Douglas Corporation, and he was one of the culprits working with Jerry Pournelle when they put together the briefing that ended up going to General Graham and then on to the White House and then came back down to SDIO. So he was involved in a deep way.
Hi, Stu Eberhard. I had a question for you guys. As you're leading into determining horizontal versus vertical, was there any technical trade studies or data that led to the decision? And do you distinguish between launch versus landing?
When we put out the original RFP at SDIO, we left it wide open. So we allowed industry to come in and brief whatever they wanted to. So Boeing came in with the reusable aerospace vehicle concept, which was a sled launched horizontal takeoff, horizontal land vehicle. Rockwell came in with a vertical takeoff, horizontal land vehicle. McDonnell Douglas came in with a vertical, but with nose entry. And General Dynamics came in with a vertical, but with the base entry concept. And all of them are valid. Every one of them came in and said, had a chart somewhere in their proposal that explained why their concept was so much better than everyone else's. I think we've learned a lot since then. And I'll tell you right now, my personal opinion is there's no way a horizontal landing or takeoff rocket powered vehicle can ever compete with a vertical takeoff and landing vehicle. But you know, those are trades done that, and those are also trades we have done in the Air Force since those early days. Anyone else have any comments on that?
No, I think just what you laid out has been substantiated by all kinds of system studies since.
Yeah, and I will tell you right now, when we did XS1, we got into all kinds of problems with slap down loads and all other kinds of loads and horizontal loads. And the problem is you don't run into all those problems with the horizontal lander until sometime after CDR. And it just kills you.
Yeah. Let's see, there's one
I
question.
I just had one other comment about the virtues of the powered vertical landing. As a pilot, I'm very sensitive to crosswinds. And one of the advantages that it is for a vertical landing vehicle like this, of course, everything is a crosswind. It doesn't matter which way the wind's blowing, it's a crosswind. But you've got tremendous amount of power to deal with that because you're using the rocket engines. I guess the thing that brought it home to me is I was flying O-1 Bird Dogs with Civil Air Patrol that lands at about 65 miles an hour, but it can stand a 17 mile an hour crosswind. The shuttle lands at about, or landed at about 250 miles an hour, and it could only stand a 15 mile an hour crosswind. So I thought, you know what? Given the need to sometimes land in bad places or in bad weather and stuff like that, I'd a hell of a lot rather fly the one that could stand a 40 mile an hour crosswind than the one that could stand 15. And we calculated on DCX and a couple of the other, and I think General Dynamics came up with a similar answer, that 40 miles an hour was not an infeasible thing to handle when you got the rocket engine power, but you sure couldn't do it with an aerodynamic vehicle.
Hey, Dan Nolan, who I think was online here, told me once that he thought he could support a 60-knot crosswind with DCX, or maybe the follow-on.
Well, Dan had his hand up a minute ago. He may be able to answer that.
Yeah, let me, this is Dan. Let me just mention one thing that I don't think was appreciated of vertical versus horizontal. And that is that with the vertical, it's powered vertical lift, and you're able to incrementally expand the flight test program. From the get-go, we could do little hops as we did with DCX, and we could have done that with our X-33 vehicle. If you looked at what X-33 was going to have to do on their first flight, they were going to have to go Mach 13 or 16 to Utah. I mean, the risk involved in that first flight was, for $1 billion investment was, I felt was, a no-go. So one of the things that got missed, I think, that in the trade of vertical versus horizontal, the fact that it's vertical is powered vertical lift. And so you can incrementally do a partial propellant load and incrementally expand that flight test program, do little bunny hops like we did with X and then kind of expand it. Whereas with the horizontal, you kind of have to get it going from the get-go because you got to get the aero going. So I thought that was one of the key trades that typically was missed. We tried to push that internally when we did horizontal versus vertical trades leading into the X-33 proposal.
So let's see, a couple questions. Thank you, Dan. Great to hear from you, man. One question, are there other programs like this? I have not seen one in the NASA world, so I'll leave it at that. What happens in the other world, I don't know about. That's a different discussion. And then how do we teach the college students about this? I know the students I've had got to hear all kinds of stories about it. So there's a small group out there that's aware of it. Maybe Jess needs to write an AIAA book or something, and then we
Well, I think what we do, I do have a briefing that I occasionally carry around to colleges and universities, and I'm willing to share it with anyone who happens to be close to a college or university that wants to listen. It's a little broader than this. It's hypersonics in general, but absolutely.
So let's see, any others? Ken, I'll turn it back over to you. I know you've got a program planned for those that are on site.
Hey, can I give you just one funny story? This is Don.
Sure, Don.
So we all knew exactly how this thing was going to land, right? Except Jim Leonard came to me and said, it's going to land on that hard stuff and it's going to catch and fall over. So we need to lubricate the deck. So we believed him and we lubricated it. The thing landed and the guys went out to get it and landed on their keister.
Yeah.
Yeah, we didn't even get to the landing stories on XA and the grade and all that fun stuff. I don't even want to go there.
It was a great idea. It was just the wrong grade.
Yeah, it was absolutely the wrong grade. CFD failed us on that one.
A minor barbecue problem, no problem.
Oh,
Hey,
well.
one more comment in reference to the vertical landing. Remember, this was a military vehicle. From the standpoint of a footprint and the area that you need to operate from, vertical landing is a lot more suitable for military operations than needing a 10,000-foot runway to an airport somewhere, especially if you want to go into unimproved areas.
Excellent point, Joaquin. And I would point out that James, all the world X-planes, about a third of them were trying to demonstrate vertical takeoff and landing. Very, very hard to do efficiently with a turbojet. But rockets love vertical takeoff and landing. If we'd had to thrust the weight of rockets when the Wright brothers flew, we'd all take off and land like the birds do today.
All right, so Ken, I'm going to turn it back over to you. Unfortunately, I have to run off and get some other things done, but I want to, Jess, thank you very much for all of your help on all this and all your leadership through the program. Jim, thank you for all of your dedication all the way through all of this, up to what we see flying with Blue Origin. Joaquin, always an honor to hear from you and always great to see you and recognize all the great work you've done. And Jeff, Mr. Laube, thank you for being a part of this and all the work you've done. And I also am going to thank Don Steinmeier and Dan Nolan online. because, and there are probably some others I'm missing, but Don and Dan, we couldn't have done it without you. And we really appreciate all your efforts, and it's great to hear both of you again, and great to maybe get to see you one day out in Los Angeles.
Fair enough.
Yeah, we should definitely plan some kind of a 30-year reunion, guys. I don't know how we do this or where we do it, but we should think about it. It's
I
coming
think
up
the El
next year.
Torito's still there.
Do we go back to New Mexico? Have they really expanded that exhibit, or are they, Jess?
I don't know. But we should
And-
get together and talk about it.
Okay, Ken, back to you.
Okay, thank you. Thank you, Dan, Jess, Joaquin, Jeff, and Jim, and everybody here. So wish you enjoy this wonderful reunion. And yeah, thank you so much. Thank you. We do have the appreciation certificate. So this is for Jeff.
You'll get one of these.
Yeah, you'll get,
You all get one of these.
we'll mail it to you. If you're not here, we'll mail it to you, Dan.
Okay.
Jess, this is for Jim.
Thank you.
Thank you.
I don't have
I
any
think
wall space left.
Joaquin, Jess, Dan will mail it to you. So really wonderful. You folks are wonderful, leading the technology and excite the next generation. It's truly amazing. And you are always AIAA. That's really one more thing that's amazing. So thank you all. Thank you very much. We do have some exhibition material on the front. So you are welcome to come out, take a look, and chat with the speaker. For folks, you order dinner, it will be here around 5:30. All right. Thank you, everyone. Thank you all. Have a wonderful evening.
It's a pleasure to see you all. Thanks for the opportunity. Thanks for putting this together, Ken.
Great pleasure.
Yep. Thank you all.
Bye.
Ah.